All right, you guys, let's get it in here. We don't have a lot of time left, so the semester, I think it went by pretty fast. Um, we're pretty much where we need to be, except for one thing. The one thing is really doing testing on the car. So this one's going to be called body electrical, but it's basic body electrical. Body electrical could be expanded into like lighting. That's mostly what we're going to do, but also power windows, power locks, power mirrors, anything that really has to do with the body. So maybe like a rear window defogger and stuff. So it's hard to cover all those things. So we're going to pick one thing. That's going to be lighting. Lighting because it's the most visual. We can understand it. We can see it, right? But throughout today, when we look at the lighting system and then we put diagrams up there, just remember, if the light bulb was actually more like a power motor, it would just be a motor rather than a bulb. You'd still test it pretty much the same. So the light bulb needs 12 volts and ground to work. The motor needs 12 volts and ground to work. The light bulb needs 12 volts and ground. The heater grid needs 12 volts and ground, right? So we can focus on lighting, and most of that will transfer to other things. And we're just going to specify this is going to be non-computer controlled. So once we get into computer controlled stuff, we approach those just a bit different. So that's not going to be what today is. And the other thing is, right here is like the break off point between electrical 1 and electrical 2. Electrical 2 is computer controlled circuits and more in-depth body stuff. And generally the diagnosis with electrical 1 is your meter, but with electrical 2, it could be the meter. It could be some of the advanced functions on the meter, but it could also be the picoscope or like any sort of oscilloscope, which ASE may call a DSO, a digital storage oscilloscope, right? So this is a really good point to end electrical 1. And also, you guys have to be ready for your final exam. So exactly what we covered today is going to be very similar to what your final exam is. You have no chance to understand this unless you've understood what we've been covering for all these weeks. So this is kind of like the capstone. You'll look at it and you'll be like, oh, this is kind of like understanding basic electricity, but also understanding wire diagrams, but also being able to use the DMM and also applying it to something specific, So I think you'll like it. So by the end of today, we should be able to go out to the cars, have a car with an inoperative headlight, and you should be able to diagnose it more than when we started on the first day when we said, what would you do? If the headlight didn't work, you take the bulb out, you put a new bulb in. You should be able to go up to it and say, like, the headlight doesn't work. Let me look at the diagram. Let me determine what should I check, what voltage should be there. If the correct voltage is not there, what should I check next, and work your way to a diagnosis. That's everything I want for you. And if you can do it, you're right where you should be. So without any delay, we start to talk about lighting systems as a whole because it has changed quite a bit. So back in the day, all the lights were like this. We may call this like an incandescent. It has a sealed chamber and like a little filament in there. So if I wanted to diagnose one of these, I take it out and I look at it like this. Like, oh yeah, that's a bad bulb. But if you look at the more modern things, it's much more complicated. Like anybody like HIDs? HIDs could be cool. HIDs, you can't check them like this. They don't work that way. They also don't work on 12 volts. So an HID, you may diagnose the 12 volt side, but then you have a ballast or like an HID controller that's going to increase the voltage and ultimately make the current flow through a type of a gas that's in the bulb. Or if it's an LED, we talked about diodes a bit. If it's an LED, we can kind of test it similarly by testing 12 volts and ground, but you can't look at an LED and tell if it's bad. So that's part of the justification for covering this pretty thorough, right? And so even a more modern lighting system going to be computer controlled. So typically through a body control module, right? So in an old car, you check the switch, click or click or click or whatever. In a newer car, that switch is really just an input to the body control module. Then the body control module is going to control the output directly, which could be like a relay, or maybe it directly powers a small LED bulb or something. So the lighting system's just really changed a lot. But it's all right. We'll cover it. So let's say we go back to the basics. The standard incandescent bulb, this is the only one that I brought because this one you can actually see. So if I look right in there, I can see if the filament is blown. And halogen is similar. It's just going to use a different, it's like this, but they'll have a specific type of gas in there that's going to help it glow brighter. So that would be like headlights and fog lights would commonly be halogen. If it's a license plate bulb, it's not going to be halogen. We don't need the license plate bulb to be really, really bright. In fact, we don't really want it really all that bright. We want it bright enough to illuminate the license plate, which is 6 inches away. If we want a headlight or a fog light, we really want that to beam all the way down the road. But we want it to be controlled. So then you can get into the housing and the aiming, and we'll talk a little bit about that, but we won't go crazy on like some of what the book covers. They really go in detail on aiming. If we just understand that if they're aimed too high, your passenger, your oncoming traffic, they're going to be mad at you. They're going to beep at you. They're going to flash their lights at you. Like you probably need to aim them lower. You could make it really scientific and get the big aiming machine that measures angles and measures all this type of stuff. And we could, and actually we have it. But for me, I would really show you how we do it in the shop, which is we basically have a little spot we pull up to and we shine the lights up against the garage door, and we typically have a little mark. And if it's not aimed, you can just turn a little thing and raise them or lower them. It's not really a big deal. But you could get really into this and look at, there's lights that actually, well, there's auto high and low beam. That's a cool function. But there's also lights that'll actually change. When you turn the steering wheel, they'll actually look a little left. If you turn left, if you turn right, they'll move. There's all sorts of crazy technology with headlights. And in one argument, people would say the headlights are too bright. And they'd say the headlights are so bright that they're blinding me and I can't see, and I need more dim headlights and from oncoming cars. But actually they did some studies and they're saying it's actually safer for headlights to be brighter so that you can see and have them illuminated. The negative is oncoming cars are more blinded. So you got some manufacturers trying out like laser headlights where they're extremely bright, but they also have a sensor where if a car is oncoming, it can detect it and it will actually dim or change the angle of the laser and keep it out of the eyes of the oncoming car. So like logically, the left side is what we're worried about because that's where the oncoming traffic is. The left one will actually lower and the right one will stay kind of high to illuminate the shoulder. You could go like really wild on all the different types of headlights and technology, okay? But we'll keep it mostly pretty simple. Let's go with incandescent. So here's a nice shot of one. You can see the filament a little bit there. That's going to be really easy. The whole reason that makes light is we're going to give that 12 volts in ground, logically. That means current's going to flow. When the current flows through this, it's going to get very hot, potentially maybe like 5,000 degrees Fahrenheit. So like really hot. It's going to get so hot, it's going to glow like bright white hot, right? So like if you have lower current flow, it's not going to make as much heat. And white hot is really hot. And if you start to get a little cooler, it starts to become a little closer to red hot. That's why when a bulb is dim, it looks kind of brown. So if you ever look at a bulb that looks kind of brown, you'd be like, it looks dim. Like we'd see it as dim, or you could see it as more reddish on the spectrum. It's because it's not flowing enough current. Maybe there's unwanted resistance in the circuit type of thing, right? And then what we'll generally do on these types of bulbs is we'll put an inert gas inside there. So that means not like combustible. It's inert. You can have oxygen burn, but you can't have an inert gas burn. So we'll put some sort of a gas in there, and that's going to help that filament last a long time. And that's going to make it so that it's pretty safe. However, these bulbs do physically get hot to the touch. So these are always going to be in a housing, and you don't want it. If you're testing a bulb and you take it out, you don't want it laying up against the carpet or plastic or something because it could burn that. The other thing is, send you back to 12th grade. The other thing is, if that bulb gets hotter than it's supposed to, it can do things like melt housings and stuff, right? So generally, if I have a bulb like this, I get the exact bulb, I put the exact bulb in, I don't have problems. Some people are like, oh, well, I found a bulb that fits. And, just because it fits doesn't mean it's exactly right. So if you have a bulb that has lower resistance, you're going to have higher amps. That's going to make more heat. That's when you can get a housing or something damaged. So the brief lesson on this is whatever the spec is, use that bulb, not just any old bulb that could technically fit in there. Okay, pretty simple. Cool. They're not very efficient though. Okay, this makes its light because we're sending a whole bunch of amps through it and it's making it glow. So if you think about it from an efficiency standard, like in a home, right? In a house, you have the light bulbs that have the filament. They look just like this. Those are very inefficient. If you understand, it's just because we're throwing amps at it. If you look at the cost of electricity, they measure it in kilowatts. Kilowatts is really just, it's watts times amps. It's volts times amps. The voltage is set, so it's really the amps that we're changing. So if you have more amps flowing, you're using more kilowatts. Get what I'm saying? So if we have bulbs that flow a lot of amps, you're going to have a high electric bill. These bulbs are bad for your electric bill. So we take them out and we put different types of bulbs that flow less amps. That's going to lower your electric bill. Fairly simple. Why do you think we would be worried about that? Somewhat, getting a little bit more worried about that in a car. Let's say specifically a car that's a hybrid or EV that we're really trying to get a lot of fuel mileage or range out of. Why do you think it would be a concern and maybe we might want to get rid of these? Which uses more gas. So that's what we were saying last week with charging was, if you're using more amps, we have to field your alternator more, which puts more resistance on the engine. Or in the case of an EV, we're drawing the battery down just a little bit faster, right? So similar with homes, we're tending to get rid of these. We're tending to go more to an LED. LEDs are the upcoming. They've been in homes for a long time, but with cars, they've been up and coming and getting more and more popular. The only negative is they're a little pricey. Now, let's say it's a halogen. So this would be similar to incandescent, but more for the bright headlights and fog lights. So it's filled with a halogen gas like bromine or iodine. So they're going to have a longer life and brighter. You need to look right here. You need to handle them carefully as they're sensitive and may be damaged even by finger oil residue. So we're not talking about like if you do an oil change, we're talking about just your natural oil that's on your skin. So if you got to change one of these, what do you think we should do? That's option A, and probably the best option is literally get a clean pair of gloves, pull the old bulb out. Let's say you're putting a new bulb in. The clean pair of gloves should have no oily residue, and that should prolong the life. If you're trying to be sneaky, you could potentially maybe change this without ever touching the glass, but it's actually kind of hard to do that. So generally, we're going to say to use gloves if it's not this type, but the halogen type. If it's a halogen bulb, you really shouldn't be touching that glass, and you definitely shouldn't be touching it without gloves.
Why does it? Sure.
It's, if you actually look at, if you touch it, that oil gets on there, and the temperature of the glass will actually start to burn the oil. And it's kind of interesting exactly why, but I know that it gets really hot on the surface of the glass, and for whatever reason that makes it fail. beyond that, it's a good question, actually. It'd be a good thing. You could come back and give us a full engineering report on that. That'd be fun. But a good question. So a lot of people know this, but exactly why? Maybe we don't know. It's a good question. All right, then we got another type, and I don't love these, but a vacuum tube fluorescent. That's actually what these lights above us are. That's a fluorescent light. We could use a little bit of that in automotive, although if we do, it's probably going to be like in our instrument panel, right? So this could be, let's say you go, I heard you guys talking about Corvettes. Let's see if you look at the 1984 C4 Corvette, they'll have little blocks in the gauges. So rather than a needle, they just have little block. It reminds me of like Atari or something. You don't know what that is? All right, some of you do, of course, of course. Rather than having a needle, it'd just be like blocks, like 1 block, 2 block, 3 block, 4 block, 5 block. That's the type of thing that may use this. We don't do this anymore. Now, obviously, if we're going to try to make a really cool instrument panel, we can use like an LCD. You know, we could do LCD with LED backlighting. But back in the day, we might use some of this type of stuff. Like, but pretty fun. All right, HIDs are, they're not really that complicated, but there's no filament in an HID. So it produces light with an electric arc. You know what we're saying there? So if we send positive to an LED, to an HID, it's going to arc to the negative without any filament. So it's got a big gap to jump, right? So if you think that it has a big gap to jump, the only way to jump a big gap is to increase the electrical pressure. And if you remember back to Ohm's law, that's the voltage. So if you want to push through a resistor, no problem. 12 volts is good. If you want to jump a big gap in an HID, you need higher voltage. You may get 10,000 volts to be able to jump that gap. Now, inside of the gap, we're going to have some different type of gas, probably xenon. That's why they'll call them like a xenon bulb, right? A xenon gas. When it jumps that arc, it's actually going to glow. It's the arc itself that's glowing because it's going through that specific xenon glass. That's what tends to give it the nice bright, almost blue light. But if you caught what I was saying, we need high voltage. So if we need high voltage, we have to produce high voltage. You guys know our automotive system is 12 volts, right? 12 volts is not enough to to jump that big gap and create an arc in the xenon gas. So we need to bump up the voltage. How do we do it? Well, the ballast is the common term. Ballast is just something that it's really a transformer, actually. We're going to take 12 volts or whatever, 12, 13, 14 volts if it's running. We're going to step that up and make it a much higher voltage that will jump the gap in the bulb. Cool. So, and they may call that an igniter. So, sometimes they have a little bulb or a separate unit on the side of the bulb. You may see something in the bulb that's like, what is that thing? That's an igniter. That's what's sending out the initial arc. Generally on these HIDs, the bulb, we're going to say the bulb itself, is not typically the failure point. It can be, but the electronics in the ballast are more common to fail. So if you have a bad HID, you definitely don't just rip the bulb out and put a new bulb in. Most of the time, that's not even going to fix it. So then we need to get more into diagnosing the ballast. It's actually really simple. Like here you can see this is your bulb, and this has the little igniter. This one, I believe, has the ballast on the bottom. But actually, I'm not sure about that. I don't think that is the ballast. I've changed a couple of these. I don't recall well enough. I might have to actually look that up, but sometimes they could have the ballast here. So this would get 12 volts. I think this one is. That's actually a pretty nice design. This gets 12 volts right here. In this little box, it's going to change it to whatever. We'll pick 10,000 volts. So 12 volts in, 10,000 volts out, and this thing up here is going to be the igniter. So if this has got 10,000 volts in it, It's going to try to send 10,000 volts here, which has to arc all down this tube and make it glow. This one actually wouldn't be a super hard diagnosis because if you buy a new bulb, you get the ballast. And if you buy a ballast, you get a new bulb. So all we really need to do to diagnose this is make sure it's getting 12 volts in ground right here at those small wires. And that may be like a little connector like this type of thing, just a small connector, and be like, oh, let me probe this and make sure it's got 12 volts in ground, and then you know what you got. However, it's also common to have this ballast, a separate box mounted like on the bottom of the headlight or somewhere near the headlight. 12 volts would go to that ballast, and then coming out of that ballast, the box, it would have like a big fat cable that would probably have a positive and negative in it, and it would go over to the actual bulb. So if that was the case, it gets a little tricky. So if you were to go to the box and test 12 volts in ground, you know that the ballast is getting what it needs to work. You would therefore know that it's not like in the wiring or in the fuse or something, but you still don't know if the ballast is putting out the 10,000 volts. So if you want to measure 10,000 volts, that's kind of hard to do, it turns out. Like you can't use your basic meter. Your meter is limited usually to like 600, maybe 1,000, not 10,000, right? So there's a couple different ways that you could measure this. You could use some sort of inductive setup, like on a oscilloscope, or what would be really fun is if you disconnected the bulb and you told your friend you need to test it, and you got it in the general vicinity of your friend. And if it arcs and shocks your friend, that ballast is good, which would mean it's the bulb. So that's one way to do it. Kind of being silly, but the point being, if you do want to test these after the ballast ups it to a high voltage, there's a shock hazard. There's like a, it's not going to kill you, but you're going to feel that.
Mm-hmm. So in a practical case, like the customer comes in with one headlight, you would just replace the ballast and the bulb.
Most likely. Yeah, we do that very commonly. Yeah, exactly. But if it was, the ballast can be kind of expensive from the factory. So sometimes the manufacturer may specify inspected in this way, right? So like each manufacturer could be a little bit different. They may say, check 12 volts in ground here. And if you have it, then it may have some special tool or an adapter or some attenuator or something to take the 10,000 and drop it down to 10 volts where your meter could actually read it. So some manufacturers may vary, but the general would be, like if it's got power and ground at the ballast, like we're probably going to just change what's ahead of that, the bulb and the ballast. A lot of times when you order them, if they're aftermarket, they come together too. So pretty unique and not really that technical. Yeah, well, maybe we could have 25,000 volts. Right. So you're going to feel that one, but it's at very low amps. That's the good thing. So when we have that transformer, we may take our 12 volts and jump it up to 25,000, which would be like 1,000% increase. But that also means we're going to have very 1,000th of the amperage. Right. So it can definitely shock you, but it's not like an electrocution where you're actually going to be injured. It might freak you out though, kind of scare you. You might embarrass yourself. So of course, because we're doing by the book, you should wear all sorts of safety stuff, high voltage safety gloves, safety boots, safety things. You have a good ground. Don't touch it. If you have a defibrillator or something, stay away from there. And that one probably is true. So by the book, by the service manual, you're supposed to be like fully dressed up to work on HIDs as if you're working on a hybrid or EV, just so you know. The practical way is probably going to be test the 12 volt side of it. And if you've got the 12 volt side good and you know it's in the high voltage side, you probably know what you need to replace. And if you wear your big yellow gloves and your full suit and you get your big arc flash shield and everything, just let me get a picture first and then continue whatever it is that you're doing. So we don't normally actually do this, but it's by the book, just so you're all aware. Just working on headlights could have high voltage. Cool, so pretty fun. And generally, I think you got it. Now let's get on to where you're going to spend more time coming up. Like I was saying, LEDs are really up and coming. LEDs started by replacing your typical incandescent because you could have this thing burning a whole bunch of kilowatts or watts, quite a bit of amps. You can pull this out, you can put an LED in, and it can be tenths of an amp. I mean, like literally 1/100th of the usage for the same amount of light. So these came in pretty strong. Then they started to figure, hey, you know what? We can do like cool little patterns and symbols. And so you guys know if you pull up on, pick a car you recognize from a distance because of the LED design on the taillights and stuff. What are you rolling up on? Oh, yeah, the Chargers. You can see the whole big outline and stuff like that. And you're like, oh, settle down. I know what that is. And then you go up next and you're like, oh, never mind. That's just somebody with a Charger. But you see, so once they figured out, hey, with LEDs, we don't need one bulb and one bulb. We can do like full circuit boards of LEDs to make all sorts of cool shapes and designs and things. And, everybody will have their favorite. That changed a lot. The reason I really want to focus on that is if you have some of these LEDs out, but some of them are working, you already know what's wrong. That gets one 12-volt supply and one ground. And after that, the circuit board splits it up and sends it everywhere. So if you have some of them working, you clearly have 12 volts in ground. That would mean it's in the circuit board. So the diagnosis can be very simple. But if none of them are working, like with an old incandescent bulb, if this bulb is out, you could pull it out and you could look at it and be like, yep, it's a bad bulb. Disconnect it, plug a new one in, and you're done. With this one, if this whole LED taillight doesn't work, that's an LED taillight assembly. You're talking several $100 to potentially several thousand. So you can't just say that the taillight is out. I need a new taillight, LED taillight assembly. It's just, there's not as much room for error when it's that much money, right? So one of the ones that I followed is the Hummer EV. And I believe somebody got in an accident with that and cracked the taillight lens. And I think it was $4,000 for that taillight. It's not even a particularly big taillight. I also had another person come to me with a Cadillac Escalade. Have you ever noticed those taillights on the new one? They're huge. They're really big. And that one was similar. Backed into something, broke the lens. Didn't want to pay whatever the cost was. They didn't tell me the cost on that, but they found something like on eBay, I believe, and plugged it in. They said once in a while it flickers. And they're like really afraid of getting pulled over. And they're like, we need to fix it. And I was sort of like, well, does a part of it flicker? Or does the whole thing flicker? See where I'm going? And they said the whole thing. So see, if a part of it flickered, that would tell me it's in the taillight. But if the whole entire taillight's flickering, that could be in like the 12 volt or the ground wire leading up to it. So it's kind of like, well, the problem is to really diagnose that, we need to measure the 12 volts and measure the ground and then like try to go drive it and hit some bumps and see, is it losing 12 volts or ground? Or if it maintains 12 volts and ground the whole time and it flickers, then it could be inside of the taillight. See what I'm saying? So diagnosing these can get a little tougher. You can't look at them. You actually have to do a measurement to see, is it getting what it needs? It's not really a big deal though. If this is your taillight connector and you know this wire is supposed to be 12 volts and this wire is supposed to be ground, you're just going to probe this one, see if it has 12 volts, probe that one, see if it has ground. If it has 12 volts and ground, it has everything it needs to work. If it's not working, it's inside the assembly. And that's generally as far as we go as typical technicians. Now, that's not to say that some, maybe one of you could become more of like a specialist where you're like, oh, if it's in the LED taillight assembly, I take those apart, I put them in the oven to melt the glue, and I disassemble the housing, and I go in and I repair the printed circuit board and solder on it or whatever, so you don't have to buy the $4,000 taillight. That's probably, you might have a pretty solid business on your hands. But for the typical technician, if it's got 12 volts in ground, it's inside there. We just say like, you need a new taillight house, you need a new assembly. And we don't go any further than that, right? Similar to ECUs. We make sure that outside the ECU is good, and if we know it's inside the ECU, it gets a new ECU. We don't disassemble those and do soldering. That's not to say some people don't, but the general technician doesn't. Right? So we could use these in all sorts of things. LEDs have a lot of advantages. Bright light, low electrical consumption. They can last 100 times longer. They're instant. In some ways, you may even make it a safety thing. When you hit the brake lights, you want the brake lights to alert other drivers as soon as possible down to the millisecond. LEDs can light up faster than an incandescent bulb, right? So you're just going to see more of a trend going to LEDs. The only negative, more expensive. So that's really the only negative. This one right here, we've taken an incandescent out and put an LED in its place. You can retrofit them. It's a good option. The only little bit of a negative is if it's like side marker lights and stuff, they're just good to go. If you replace an incandescent bulb with an LED for a turn signal, a lot of times it'll make the turn signal flash fast because it has so much resistance on the LED, right? Now think about what I'm saying. If it has a lot of resistance on the LED, that's kind of like an open, right? And you guys have seen if a car has a blown turn signal bulb, the flasher flashes fast. A blown bulb is an open. An LED has such high resistance, it kind of makes it look like an open to the system. So if you put LED turn signals in, your turn signal starts flashing fast. You got a couple of options. Probably the best one is to replace your regular flasher with an LED or a heavy duty flasher, and that'll just flash at the correct rate all the time. Some people will choose to fix that, some won't. But that's simply because of difference in the resistance, which means if it's got a lot more resistance, that's ohm, right? Ohm is pulling up on that rope. That means less amp is going through, correct? Well, that's a good thing because amps cost money to produce through an alternator, through a battery, through whatever, but can make the system flash fast. I've also seen LEDs are really nice if they're bright white for reverse lights because you can see better. The negative is sometimes the way that the reverse camera, the backup camera comes on, depends on the exact voltage drop on the bulb. And if you put an LED bulb in the reverse lights, all of a sudden your backup camera may be on all the time or not on at all, and it's acting weird. So customers come in with, my backup camera's funny or whatever, and if I look and I see LED bulbs that were not supposed to be there, I take those out, I put the regular incandescent bulbs in, and all of a sudden all the backup camera stuff is resolved, and it's like, well, you might have to talk with a company who figures out exactly what inline resistor, or there's going to be some fix to get that backup camera to still work. But I've seen in multiple occasions where just throwing an LED in there will mess that system up. Just be forewarned. Now, if you look at the LED, they only really want like 1 to 3 volts to be powered. So if you want to throw an LED in, you're looking at this assembly. Inside of this LED, there's got to be some additional circuit. Like it could be a resistor, but a lot of times we'll pulse the LED. So it may be, pulsed at a frequency where if you walk up to it, it's on, right? But you ever notice if you take a video with your camera of LED lights, they're flickering and you're looking, they're not flickering, but you look on here and they're flickering. That's because technically those LEDs are actually flickering, and they flicker so fast your eyes can't see it, but your camera takes a sample rate, and once in a while they're on and once in a while they're off, and that'll actually show up on your camera. So these bulbs typically have a little bit more going on in there. That logically would make them more expensive, right? So we're actually pulsing that and controlling some things that's going to be a little more pricey, but I'd say still overall, it's generally an improvement. And then one thing that I've seen people get a little confused is dual filament bulbs. Why do you think we would want a dual filament? True, one's brighter and one's dimmer, so why do we want both though? High beams could be, but if you look at this style, this is more of an incandescent. An incandescent wouldn't make a good headlight. That could be like a halogen. And halogen could, we do high and low beam in a few different ways. But for this is going to be most likely either a turn signal or a stoplight / tail light. So if you have the tail light on, this might be the dim filament. And if you hit the brakes, this one will come on either additionally, or rather than this one will come on. That'll make it more bright, right? So if you look at a car and the tail lights are the brake lights, they just get brighter. It's most likely because of a dual filament. The reason I bring this up is if you have one filament that blows, that's going to take out either the brake light or the tail light, but the other one could still work. So sometimes people are confused, like, well, the tail light works, so it couldn't be the bulb. Well, it can be. If one of the filaments blows and the other one's still good, it can absolutely be in the bulb. Other time you'll see it is, sometimes it's like a turn signal and maybe like side marker, right? So you have a light on to show the side of the car, and then if it flashes, if you put the turn signal on, it'll flash a brighter one. Right, so you could see some of those dual filaments sometimes too. If it is a headlight, it could be a dual filament, but it would be like a halogen style on a newer one. We also used to have sealed beam headlights, which were dual filament too. I think I got one for one of those. Cool. So if you look at this one, you'll notice this has one contactor, right? If it's a dual filament, there are a lot of times be two little bumps right here. So this is generally where your positive goes. And then this goes into a socket, and these little lugs right here, these little pins are what's going to hold it in, but the ground is going to be on this part of the housing. So if you're working on this is older. If you're working on something older and you can see there's corrosion here, that's a problem. If there's corrosion here, that's a problem. This is the male part that goes in the female part. If there's corrosion on the socket, like, that's a problem. All that corrosion is unwanted resistance. So these were really common, but we mostly don't use those. Sometimes we'll call this the blade type. The blade type just goes in like this, click. This is a little more common now, but those used to be common. You'd have to push down and screw it in, and it was a little spring-loaded thing to make sure it had a good contact right there. Right, so not a real big deal. Okay, so like here's a typical bulb, 194. So this is a wedge style, right? Not a bayonet style, but a wedge style, which I called a blade type, but we'll go with the wedge style. This is just gonna squeeze into a couple, well, basically a plastic connector, which will have maybe like a positive female terminal that engages the male right here, and a negative female terminal that engages the male right there. By the way, if you change these to LED, remember an LED is a one-way valve. So if you put an LED in and it doesn't work, take the LED back out, flip it 180, plug it back in. It'll probably work because the LEDs are one way, whereas this could be bi-directional, if you will. And then a festoon would be more like a maybe a dome light or something. Right, so a few different types there, just so you know. All these have their positives and negatives. Kind of the positive of the festoon is the terminals can really grab it and hold it. So it's nice when it's up here and you just click it in. That's pretty good. And that's convenient for a dome light because you just pop the plastic cover out, pluck the bulb out of there, and pop a new bulb in. Of course, they make retrofits for LEDs for that too. Right, it's just different. And then when you start to look at the overall lighting system, we want to make sure we use the right terms. So if you walk up to the car, everybody knows headlights, everybody knows taillights. But sometimes the lights on the side, people aren't exactly sure. So generally, headlights, taillights. Of course, brake lights can be combined or separate from taillights. But let's just say for now, the taillights, two taillights in the back are also the brake lights. You ever notice there's a brake light up in the middle? A center high mounted brake lamp. Good. What about on the side? There's something on the side typically. So like commonly, if it's got some sort of side light, the back ones would be red and the front ones would be amber. There's a reason for that. That's telling you which direction the car is facing too. So like if it's at night, it's hard to see. If you had red lights on the front and the back, you don't know which way is front, which way is rear. You don't know which direction it's traveling, right? That's why if you decide you want to put red lights on the front of your car, you go and get a ticket because that's against that's against the law. Back of the car lights are going to be generally red with the exception of reverse lights, which are white, and typically license plate lights, which are white, but they're not that bright. So it's not that confusing, right? On the front of the car, you're going to have white lights, not red lights. And you're also going to have amber to mark the corners, which a lot of times will be like a side marker light, a corner lamp or a side marker light. That's just to give you the outline of the vehicle so you can really see it in the dark. And so for that reason, hopefully you guys will understand why we don't have you want to do European Altezza tail lights that have white on the back. And it's like, no, that's not the tail lights are red. The tail lights are supposed to be red. They need to be red. It's also part of the reason that we don't do like all sorts of creative colors. Like maybe I want my taillights to be purple. Maybe I want my taillights to be green. Like, no, that's not how this works. Everybody can't have their own self-expression. You can wear whatever color socks you want. That's good. You just can't have whatever color taillights you want for motor vehicle traffic safety, right? That's the goal. And then that's kind of what we're talking about. Park taillight, marker lights. They're all going to be pretty low intensity. So here, for example, you can see you got license plate lights. Those, by the way, should not be blue because blue is supposed to be an indication of law enforcement. Makes sense? If you ever notice, even the ambulances and stuff, those aren't red and blue. Those are like red and white flashing and horns and fire trucks and stuff like that. The police are the ones that use the blue ones. So we're not really supposed to be having blue LEDs, and you're definitely not supposed to be having them flashing. Okay, so I've seen it, but not a good idea. These are generally the only white lights that should be on in the back of the car, and they're going to be facing downward. Parking lights, for example, now we could break it down. This inner one is a parking lamp. This outer one is a side marker. This may be hard to understand, but if you're pulling over and you're going to park in an area where there's a lot of pedestrians and people and activity, you could turn your headlights off, but not all the way. You could turn your headlights off and just have that very first click, right? When you turn your headlights on, it goes click, click. The first click is parking lamps. If you're sitting at, where are you sitting? The drive-through at In-N-Out, of course. You could chill a little bit, turn your headlights off, just have your parking lights on. So that way people walking, pedestrians can see you, other cars can see you. You don't just have to sit there with your high beams on or your headlights on and everybody's like, I can't see anything. They're parking lamps. They're so that you can park. Now, if you're driving, they're not driving lamps, they're parking lamps. So just be aware. That's why they exist. Educate your friends and family. Hey, we're in the drive-through. Let's chill on the headlights a little bit. Let's have the parking lamps on. That's what they're for, of course. And if you move forward at a mile an hour because they just moved through the drive-through window, you don't really have to put your headlights on. You can just roll up nice and slow with just your parking lights. You'll blind less people. Everybody will be very happy with you. Then you'll forget to put them on and you'll pull out and you get a ticket. Ha ha ha. And you deserve it. All right, pretty good. And then here's a term, parallel. I think you guys will remember. So generally when we say that the bulbs are connected in parallel, we're talking about you go to the headlight switch, you turn the headlight switch on. That one headlight switch goes down a circuit that's going to split and the two bulbs are connected in parallel. So if you have one bulb that doesn't work, it's not going to be the headlight switch because they're wired in parallel. Or if you have a bad headlight switch, it's not going to make it so that only one bulb doesn't work, right? So just understanding how the circuit's laid out. Then, of course, we won't go real crazy, but on a computer-controlled system, park lights, tail lights, brake lights, all that type of stuff can be controlled by the body control module, which can be helpful in several ways. Like, you guys ever seen the videos where a car gets in an accident and all of a sudden the flasher lights are on, the emergency hazard flashers? You think that driver is so with it that they're like, oh, I just crashed my car, let me put on my hazards so that nobody hits me? That ain't why those came on. Those came on because the body control module just got a signal saying, we just crashed and we should make it as safe as possible by putting the hazard lights on. And the customer is unconscious or out of it. So let's just have the computer take over and put the hazards on. Kind of makes sense. That's really what's happening there. Then, of course, side markers we talked about a little bit. And then you could get into some more details, like it can be cool to have turn signal indicators in the mirror. It can also be cool to have side markers way out on the side. What's really interesting is if a vehicle's over a certain width, I don't remember the number, but let's put it this way, an F-150 is not, but an F-150 Raptor is. They have to actually start putting the 3 lights in the center of the vehicle, because on the Raptor, you know, it's got the wider fenders in the body. If you got a side marker here and a side marker here, it could actually look like maybe it's like 2 different vehicles. So they want 3 lights in the middle. That's a DOT rule. So the Raptor has it. The Hummer EV has it. Some of the really wide, I think the Bronco Raptor might have it too. So if you ever see like some of the really wide ones have 3 orange lights somewhere, you'd be like, that's cool, but that's actually required. So when people put them on the Tacomas, they're just trying to look cool. Like, you don't need it on a Tacoma. Pretty fun. Right, there we go. Here's a good shot of what we may call the Chimsel. See this? Chimsel. Center high mounted stop lamp. It has to be centered. It has to be higher. So in the trunk, in the wing, in the rear window, up by the roof, that's all fine. Depends on what style you like, but it needs to be centered. Cool. Now if we were to look at, go ahead. I think it was 90s. It was like early to mid 90s. They don't. And so that's a fun point. Whatever the car model year was, it's held to those standards. So if you buy a car that's old, you don't have to have any of the things I just said. But as the vehicles are being produced, if they make a rule, let's say in 2030, that every vehicle has to have LED lights, that means model year 2030 and forward has to have LED lights. It doesn't mean a 2025 has to have them, right? So if you have like a similar one to that would be, when I was a kid, I had a 68 C10, and in 1968, you could have either a rear view mirror like this, or you could have door mounted rear view mirrors. And if you wanted to have a really clean body, you could take your mirrors off and you could just have this one. Or if, let's say, you wanted to have like, like if you wanted to have the back window super blacked out, you could actually paint the whole back window, and you would just need to have those outside lights. So there was like different rules and regulations at the time, similar to lights. But it's just mostly pushed on the manufacturers, and it has a lot to do with National Highway Traffic Safety Administration. So that'd be a government agency, NHTSA, that says, hey, we did a study. We found that it's safer for people if you have this thing. And then they don't run around telling you. They go to the manufacturers and you're like, you better manufacture that car with this thing now. So this is mostly a manufacturer concern. But any light, and here's really the law, because some of you are going to get pulled over. You're going to have an argument and be like, well, I don't need a center high mounted stop lamp because I know of my other car doesn't have it. If it's equipped on the vehicle, it needs to work. Now that has a little bit of a gray area. So if the car came with a light, it needs to work, period, because it was to that standard. But let's say that you took this Ford Focus and you put a big old wing on there that has a light, that has a lamp in the wing. then it's sort of like, does it need to work? Does it not need to work? It didn't come with it. So does it, it gets a little bit tricky. I think that if you were to get pulled over and get a ticket and this light worked, but you added a wing and that light didn't work, I think you could actually win that case, but you're still probably going to get a ticket and you're going to have to most likely go and study the whatever California vehicle code or the whatever the federal stuff is and be like, see, it says here this car wasn't equipped or something. So generally, if you want to not have a problem, if the light's on the car, it needs to work. Then you really can't get a ticket for it. They cannot pull you over and be like, hey, you have a 55 Chevy, you need a center high mounted stop lamp. It didn't come with that. That's not a law if it didn't come with it. Not that any police officer would ever do that, right? Of course not. Of course. Okay, your first diagram. Here's what we were talking about with, they're in parallel, right? So if we look at this diagram, we got 12 volts coming in through a fusible link or a fuse or whatever. It goes to the brake lamp switch. If you don't have your brake pedal depressed, that switch is open. So this is a normally open switch. And this is kind of somewhere between a diagram and actually an illustration that shows the pedal, which I do like. When you push this pedal down, do you know what happens to this switch? It closes, which means your 12 volts came down. Now that you've pushed the pedal down, which we call depressed, depressed means you push it down. It's kind of like, if you have your hair like this, you're like, it's not a phase, you're depressed, like you're down. Like that's what depressed doesn't mean unpressed. People get really stuck on that. They're like, well, the pedal was depressed, which means it isn't pressed. I'm like, no. Depressed means push down. Okay, we're good. It's a phase, trust me. So if it's depressed, 12 volts goes through the fuse, through the switch, and look, it goes to this point right here, and that's a splice. And after that splice, it splits off into parallel. It goes through one bulb filament, through the other bulb filament. Now you notice these are dual filament bulbs. If this is the stop lamp filament, and this is the stop lamp filament, what do you think the other filament is? Yeah, exactly, just the taillight filament. Bingo, right there. Exactly right. Oh, and of course, backup lamps. Yeah, backup lamps on Dwight Schrute's Fire Chicken featuring. No, he had an older one. This is a nice Trans Am. These ones are kind of cool. They had nice, brighter backup than the Camaros did, but backup lights are the only thing that should be white. So if there you are walking through Costco parking lot and you see some white lights shining out the back of the car, that's the one you don't want to walk behind. Because if the white lights are shining out the back of the car, it's in reverse, right? Now, sometimes when you get out of the car and you press lock, they'll program the BCM to shine the backup lights just to give you some illumination so you can walk around and not trip. So I've been burned by that before where I'm walking, I think I'm really smart, and I'm like, reverse lights are on, I'm waiting. And people just walk right by, and I'm like, don't you see the car's in reverse? And then I realized, no, they just locked it, and it put the reverse lights on for illumination, and they're already halfway into the store. And I'm like, oh, I look like an idiot. So once in a while, I get burned by that. But most of the time, if I see these on, I know. You know what the giveaway is? If you see the white lights on and the center high mounted brake lamp, they have their foot on the brakes and it's in reverse. Steer clear. That's what I'd recommend. Cool turn signals I think we got. Now look at this car. That is an amber turn signal. So I was saying the back of the car is supposed to have red lights, but sometimes turn signals could be amber and sometimes they could be red. Either one are legal. However it came is how it's supposed to be, but they're so all over the place. Like if you were to buy some Euro spec taillights and have them be amber in the back, that's fine. You're not going to get in trouble, but that's approved. That's good. If you buy some Euro spec taillights and you make this turn signal blue, you're going to jail. That's a for sure thing. But amber is fine or red is fine, either one. Of course, you know how we turn that on. We went ahead and we put the turn signal switch on, and then the flasher uses some sort of timing circuit, maybe 60 times per minute. That would be every second, right? Or some of them are a little faster. So every turn signal could be programmed slightly different, but that's your range right there. 2 times a second or maybe 1 time a second flash. If it's messed up and it's flashing like this, some people will call it hyper flashing. There's something wrong. Probably a bulb is out. Right? So this is an electronic circuit. Older cars had a thermomechanical flasher that would literally heat up an element and touch, or it would cool down and touch, and then when it would heat up, it would separate, and it would cool down and touch and heat up and separate and cool down. It was purely mechanical. That was the thing that made the clicking sound. It was the expanding and the heating and cooling element. Then those were not really that reliable, to be honest with you. When we got rid of that and we went to something that was basic electronic control, people were like, oh, I missed the sound. I didn't realize that my turn signal was on the whole time and I forgot it. It didn't make a sound. We started actually putting the sound back in through like a little speaker. Sometimes you run the sound through the speaker. Right, so fairly simple how that went. It was mechanical. Now it's a little bit computerized. And then you all understand the hazard is the 4-way flasher. So if you have a problem, let's say you got a flat tire and you're on the side of the road and you want people to see you, but you don't necessarily, if you shut the car off, you don't necessarily want all your headlights and taillights on. That's going to drain your battery a little fast. The hazards are more like battery powered. You don't have to have the key on. If you just push the switch, it's just going to flash all 4 corners. Should be pretty attention grabbing, and it should not draw your battery down too fast. It also could be used as an indication that there's something wrong, like you're on your way to the hospital, you had too much Taco Bell, you rapidly need to find a rest stop, these types of things. You put the flashers on, you have to hurry up, get out of my way. These types of things, just to alert other drivers, really. Also, if you see an accident and you know it's hazardous to other drivers, it'd be a good idea to put those on. And that's how those are supposed to work. The hazards are funny, though. Sometimes if you have the hazards and the turn signal on, every car can do something a little different. Like, ideally, to me, if you have the hazards on and a turn signal, I would actually have the turn signal supersede the hazards, because at least people know you're turning in. But not all cars work that way, so there can be a little bit of a difference. Cool. Like I was saying, if it's BCM controlled, they can turn that on at any time. So that pretty much gets us through the exterior lights. Now onto some more interior lights. These are all lights. This right here, if you look at the colors, we got red, 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 amber, amber, red. That right there is what everybody calls the Christmas tree. That has a Christmas tree on. If you get in the car and there's all sorts of lights on and all these, it's like Christmas. It's decorated. It's fun. That's a Christmas tree. So somebody ever says, yeah, I got on, there's a Christmas tree on the dash. They could be, but they're most likely not talking about any sort of a evergreen, any sort of plant life on the dashboard. They're probably talking about a bunch of lights that are illuminated. So this one has time to buckle up. This is an airbag light. This is a brake warning light. And that's the red one. That's not a good one. That could be the parking brake, but it also could be brake fluid or hydraulic failure. The ABS light, the check engine light, and the genie lamp, of course, which means somebody has got 3 wishes and one of them should probably be a new car because you have low oil pressure. That's the oil pressure light, right? So that's a Christmas tree right there. We also have backlighting on these gauges. So if you were diagnosing something like this, generally it's got nothing to do with lighting. But if one of these lights, for example, didn't work, we would diagnose those just like we diagnose a tail light. You'd see, does it have 12 volts? Does it have ground, right? So if you had a car and when you applied the parking brake, the brake light didn't light, you could diagnose that problem with the parking brake light just the same as a tail light. It's pretty simple. Similar with a lot of these. Most of the time we see these on, though, it's because it's indicating a fault and we need to diagnose that fault, of course. Right, so probably pretty, oh, you know what? I jumped the gun. I forgot. I did have one addition. This is an older style headlight. We did have these headlights back in the day. It was like a sealed assembly. They could be round or square. We could have some sealed beams. Those were interesting. And this one has the low and high beam are in different positions. If you look at the low beam, you notice it has this big like shield over it. That's to basically take the light, bounce it back, and then you're really seeing the reflection of the light, and it tends to be more scattered and less direct. So that'd be low beam. Whereas the high beam, a lot of times that'll be like unshrouded or unshielded, and that's going to be in your face. That's one way to do it. Some other crazy ways that we've done it is, let's say, here's a car you probably wouldn't really know, but it's the one I just thought of in my mind. We had a thing called a Buick Enclave, and they had some of the earlier HIDs. And it only had one HID bulb, because if you have a high and low beam HID, you got to have like double the ballast, and they're kind of expensive. So what this Buick Enclave did, which is pretty much like an Equinox or something, or an Acadia maybe, if you had low beams, the HID was on, and this opaque shield would flap over top of it and just kind of make it less bright. Then when you did high beam, you'd hear a thunk, and this thing would flip up, and it would just give you the full HID. So we could do high-low beams through one filament and another filament. We could have, one filament that's shielded and another one that's direct. We could have even covers that potentially that basically make it a little bit more dim. The high and low beam can be controlled in several different ways, but probably the most common is there's a high beam bulb and there's a low beam bulb. The low beams are typically on the outside and the high beams are typically on the inside. So if the low beams are on the outside, the high beams are on the inside, and somebody pulls up to you and you're like, hey, those lights seem kind of bright. Is it high beams or low beams? You can't tell. Well, look, if it's the inside, those are high beams. So that's your chance to beep at them and be like, hey, that's not nice, or something, whatever you want to tell them. It's a good indication. Not just the brightness, but the location can give you a pretty good clue. All right, pretty good. Now, automatic. So we are mostly through the basic lights. I think I got a little bit with daytime running lights and stuff, but if it's automatic light system, who's got automatic lights in their vehicle? You guys are fancy. I actually really like it. Back in the day, it was pretty common that people would forget to turn their headlights on, and it was kind of scary, or forget to turn their headlights off, and they need their battery jumped. That was just all the time. So if we're looking at safety, have them turn on automatically. If we're looking at improving the customer's sense of reliability, have them turn off automatically, right? So they can forget and become even more brainless, as our society has year after year after year. They have less responsibility and less things to think about, and they become mentally lazy. But we'll focus. The car does it for them, so that's really nice. And I'd pay more money for that car. And if I was a manufacturer, I'm going to implement this so that people want to buy my car because it's easier. Cool. But also, if I have them turn off and it doesn't kill the battery, overall they're going to have a sense of like, hey, I like that car. You forget your headlights all the time and they turn themselves off and you never need to jump. I like that car, right? So that's the main push. It's safer, lazier, and also more reliable, which just basically covers for distracted minds. So if that's the case, all good. But how do we do it though? Right? Like back in the day, the original on and off, you'd have to turn them on, but if you left them on and it saw that the key turned off and then the door opened, that would be an indication that they forgot and it would turn them off. So some of the old Toyotas would turn themselves off when you open the door. But a full automatic system, computerized, right? So without jumping into full computer controlled circuits, we'll just discuss it as a whole. The computer, probably the body control module, looks at a bunch of things. One of the main things is going to be, what's the current ambient lighting status, which means we need a sensor. It happens to be like a photodiode. Put a little bubble out in the dash. It measures how much light there is. If there's a lot of light, do we need the headlights? No. But if that sensor doesn't read a lot of light, that would be a good time to turn the headlights on, right? So then all we really have done is kept mostly the same circuits in place, But rather than having just the switch control it, the switch becomes an input to the computer. The computer also looks at the ambient lighting sensor, the solar sensor, and then ultimately the computer has the ultimate say. Turn these lights on, turn these lights off, turn those lights on, turn those lights off. That's automatic. That's it. It's that simple. If you try to diagnose it, well, that subject is really for next time. We do computer controlled circuits, and then the way I give you just a sneak preview right at the end, showing we need to check for codes. We need to use the scan tool. There's a little bit of a different way to diagnose. With regular lighting systems, it's going to be all about checking 12 volts, checking ground, using our meter, using the wiring diagram. So that's what we're going to stay focused on. Although it's fun. You like that one, huh? It's a good car right there. Well, it's in Illinois, so it's probably pretty rusted. But this one was a really good one for showing some fog lights or driving lights. So if we were to say driving lights, that can mean a number of different things. Typically, if it's a driving light, what that means is you start the car, the driving light's off. You put it in drive, or you start moving, the driving light comes on. Why do we have it? Well, it's supplemental. Mostly, though, it's for visibility, right? It's maybe higher illumination, but it's also for visibility. So if you're driving around, and basically what they did, NHTSA did yet another study, and they're like, hey, you know what? You don't need the headlights on during the day, but if you have lights on during the day, do you think you're a little bit more likely to be seen so someone doesn't pull out in front of you? So that's mostly what driving light, or we could even roll straight into daytime running lights. That's their main function, is to help you be seen so someone doesn't pull out in front of you or something. Motorcycles, so you know. Motorcycles after, I don't know the year. It's been a long time, since like the 90s. All motorcycles, when the bike is running, the headlight has to be on. Any motorcycle you ever see, you'll notice if they're riding, the headlight's on, unless it's old, in which case that's how you know it's old. So one of the things when I went to bring some of my dirt bikes to DMV to try to do a dirt bike to road legal conversion, one of the things they want is, when you start the bike, does the headlight come on? And I was like, why are we worried about that? And that's why, because in the regulation it says after this year, when the bike starts, the headlight has to be on. It's just to make the motorcycle a little bit more visible, because, you know, they be getting killed and stuff. That's just what happens. I know about that. So these types of things have been a trend. They do some study, they find out it's safer. Now they do that. Now that's the thing. Yes, I did figure out a way to get the headlight to come on every time the bike was started. I did get my license plates. Thank you very much. Just had to make sure that I met the regulations. All right, cool. So they could be all sorts of different style, but generally it's gonna be like 55 to 120 watt range. So it's gonna be, you know, bright, but not necessarily super bright. So if I were to break off of this one, I just want to check something real quick. I think I have DRL. No, I don't. So I'm going to bump DRL with this just because I was thinking about it. If we are talking about the driving lights, now I want to add daytime running lights. Those are pretty much the same thing. So maybe the driving light typically is going to be more when you're moving, and the daytime running light is typically going to more be anytime it's running, but basically they serve the same purpose, is to increase visibility. What's kind of funny about DRLs is a lot of times we'll have the daytime running light will run through the high beam, but it won't run through the high beams in parallel. It'll have some sort of a DRL relay that'll switch. And this isn't necessarily it, but if we had the daytime running light diagram up, a lot of times what we'll do is we'll run power to one high beam and then wire it in series to the second high beam so that they each share 6 volts. And so that'll use an existing bulb. We don't have to add a bulb. We don't have to add a whole bunch of wiring. We really just rework how the relay is wired up. And if that relay is closed, it puts it into series. I actually never loved diagnosing a daytime running light fault because the wiring was just weird, but that was a good way they did it. That, however, is mostly gone because we've gone to automatic headlights. And the other thing is, you guys have seen the cool LEDs in the front that make cool shapes and pretty little looks and stuff. Those are not truly DRLs, but some people will call them daytime running lights, or they could be driving lights. It's used pretty interchangeably. Any car that has the front LEDs for running lights, that's going to be computer controlled stuff. So we're not doing like the series high beams anymore. We're just having the body control module know that the car's running and it's during the day, and it's going to turn those running lights on instead. Now, if it gets dark out, it's not going to probably run those running lights. It's probably going to run the headlights. Sometimes it might run both, right? So if a car rolled up, like, you guys know what I'm talking about, pick a car that has some crazy LEDs in the front during the day. Not the headlights. You know the one I'm talking about. Oh, what do those look like? The halos? That's too old, huh? Yeah, what do they look like? I don't remember those. Oh, the parentheses, like this. Yeah, exactly. So that'd be a running light. What else? You guys got to have your favorite types of cars. I noticed the new Camaros have they do a little shape. Probably the Mustangs have something. I just don't remember what it is. I also noticed a lot of Audis have like a long thing that's underneath. The Hyundais have their own, right? So those can be kind of a design feature, but really what it is, it's a running light to improve the visibility of the vehicle. That's what it actually is, right? That'll help the insurance rates. Then, of course, fog lights. You guys know what fog lights are actually for? Yeah, that would make sense, wouldn't it? So, yes, the fog lights are supposed to be low and give you kind of a wide spot, a wide floodlight, not a spotlight. They should be wide so you can see low. I know that the yellows are pretty popular, but you'll notice they don't come yellow from the factory. That's like an aftermarket add-on. I don't know if people are getting tickets for that, but generally from the factory, they're going to be white or pretty close to white. Here's a fun fact about fog lights. If they're from the factory, your only time you can have fog lights on are when you're in low beam. If you put your high beams on, you ever notice the fog lights turn off? That's from the factory. That's like a DOT standard. So we don't want your brightest headlights and your fog lights at once, because that's not really what the fog lights are for. The fog lights aren't really made to give you maximum light. They're made to give you light from a lower angle and kind of broad, right? It's supposed to kind of be low to the ground so you can see, not so you're blinded by the fog in your face. So that's another pretty cool feature. I like them. And then the other thing is, look, it's got a sharp cutoff pattern. So it's supposed to remain below the driver's eye level. Now, if we were to go right from there and talk about the cutoff style, there's different types of lights. Reflector is old school. That kind of throws light everywhere. It's not real crisp or real clean. But projector type, have you ever noticed projector headlights? They can have like a line where above the line is black dark and below the line is very bright. That's traditional of a projector. So if you have a projector style headlight, that's when you can get away with having those really bright lights. If you have LEDs and you throw them into a regular reflector, a lot of times the LEDs just throw a ton of light out and everybody's like, I hate you. Like, beep, honking, high beams. And you're like, my low beams are on. But if you throw those LEDs, those don't have a real controlled beam. They throw a ton of light in on a reflector. It bounces it everywhere. But if you got a projector, those you can run really bright lights and not blind the driver, but really illuminate below the driver. So the projectors are cool. Those are the ones that tend to have like a round housing inside. You can notice they have a certain shape. These are very critical to aim properly, because if you have them aimed too high, it's very, very bright. And if it's up in the oncoming driver's eyes, it's going to be problematic. Right. And then the sealed beam is like the assembly. So when we talk about aiming, we're literally talking about basically the angle of this bulb. So sometimes it's changing where the bulb is mounting. in other times, it's actually changing the whole position of the housing. But either way, it's going to change the angle of the bulb, and we don't want it to aim too high and we don't want it to aim too low. If it's too low, you can't see far enough. If it's too high, actually, it's kind of nice to drive, but everyone hates you. And if everybody aimed their headlights too high, nobody can see. You know, like the whole eye for an eye leaves the whole world blind thing, that would apply. So doing the aiming is to give you maximum visibility without impairing the oncoming driver's visibility. Right. And then the sealed units, not really a big deal. That was the old school. The whole big housing, which it would be like an assembly like this. You couldn't change the bulb. You have to get the whole glass housing. It was kind of old, but it was fun. I think we're pretty good on HID, right? But LED, we're doing more and more of those in the front. Those, well, I mean, they're working really good, but they're very expensive from the factory. And a lot of times they come with projector housings, and those are kind of set up. So from the factory, they're good. If you're adding LEDs in the front, they can be good, but you have to have a way to aim them. And some of the LED bulb manufacturers, like the Chinese ones, you can't aim them. You just put them in there and they look cool to you, and then they don't actually improve the performance. But from the factory, if they're coming with LED, they're pretty nice. A lot of times those could have heat sinks or fans if they're LEDs, because LEDs actually don't make as much heat as an incandescent. But if we start to do a lot of LED chips to give maximum light, they can start to make a lot more heat. So they'll have like an aluminum heat sink, or they could have potentially a fan. And if you really want to get technical, there are some cars that come with night vision. I don't know if you knew that, but they do. There's some that come with night vision. Cadillac was really big on that back in the day. You could actually put it up in the center console or in the instrument panel, and you couldn't necessarily drive with no headlights, but like if you were driving down the road and there was an animal on the side of the road, your headlights might not be able to illuminate it for you, but if you were to glance down at your instrument panel, you could actually see something, and night vision would pick it up. It was a pretty neat system. And there's various different versions of that. So sometimes you have to turn them on and off. Sometimes they're just there and they'll give you an alert, right? And they would use infrared typically. Infrared's interesting. Your eyes won't see it, but the infrared will pick it up. It's kind of like how trail cameras work. The animal might not even see the light, but the infrared, because it's at a certain wavelength, will detect it, and then it can reproduce that on screen and show you. It was pretty cool. And then the ideal is if it has a heads-up display, and it can actually project it up onto the windshield and give you a clue that it's there. That's really cool system. Right? Or they have heat sensing, have all sorts of stuff. Pretty fun. So I think you were probably pretty good on this part. And we could go, there's a lot of different peripheral type of lights too. Okay, but I think we're solid on that. All right. Talk about aiming for just a moment without going really crazy. Here, we want to aim these headlights. So again, if you aim them too high, you're blinding drivers. If you aim them too low, you as the driver would not be able to see that well. So what I would do is I'd roll this up to the garage door, and we have a little mark, and we can aim them, and they turn out pretty good. But if it was, let's say, a collision shop that's dealing with it after an accident, they would be more likely to have this tool, and you roll this tool up, and it actually has a certain distance that you set it to the car, and you're going to turn the headlights on, and then you can look through this and you can see exactly where the lights are being aimed, and you can fine tune it. So see, it's projecting on this diagram, and it's going to say at this angle, at this height, in these specs, which would be in the service manual. And then from there, you could go over to the car and turn a screw or turn a bolt or turn something. And you could raise it up, raise it down, go a little left, go a little bit right. It's cool. It's a little technical. The main reason that I'd say it's most common in a good body shop or collision place is the car's in an accident and all that stuff is bent, and they get it straight and it should be within a millimeter. Then when you put the headlights in, they're probably new headlights. You just really got to make sure that everything is dialed in because you had a lot of stuff apart. For us, we don't normally have to aim headlights. If you unbolt the housing and bolt the housing back in, it shouldn't change. If you put a headlight bulb in and all of a sudden the aim is way off, I'm going to bet you don't have the headlight bulb seated correctly. So aiming is not something we do every day. However, who likes their car lowered versus who likes their car or truck lifted? On the ground. And if it's on the ground, that's fine. But think about this. If you lower it, now you just potentially lowered where your headlights are pointing. Your headlights also may be on the ground. Or what if you lower it, but you lower the back a little bit more? Now you're popping a little wheelie. Now your headlights are up in the trees. Or similar with the truck. You guys know about, what do they call it? The Carolina squat, right? So if you do that, all of a sudden, if we're messing with our suspension, that's what would prompt the headlight alignment on the technician side. The body shop is dealing with it more from an accident collision standpoint. But for us, if you're changing your suspension angles, that's kind of like when we would deal with it. Or let's say it's a Range Rover and you put a bunch of junk in the trunk, it actually measures the angle and the air ride should maintain the angle. So when you have air ride, it should maintain the angle. That's nice. But if you don't, there's some cars that measure the angle of the suspension. It can tell that you're popping a little wheelie. It'll actually have an electric motor that will turn the headlights down. They have some wild technology to try to keep the headlights aimed when your suspension angles change. For most of us, if you change the suspension, the ride height, that's when you want to take a look at that angle of your headlight aiming. Cool. Not really a big deal. So overall, probably pretty good. You guys will understand. Headlights, overall, I think good. So if someone puts aftermarket bulbs in, we talked about this in the beginning, silver stars, for example, those could potentially be technically illegal, but more of my focus would be if the silver stars flow more amps, that's going to be harder on your connectors and they can tend to burn the connectors, right? Melt the housings. So again, we're really recommending direct replacement, factory replacement. Keep it stock. That's what I'm saying. All right. So from here, we're going to look at a lot of diagrams. The diagrams are going to explain the lighting system a little bit, but mostly we're going to talk about how to check it now. We're going to diagnose it. So if I were to give you a little heads up, I would say when you start to see the meter on the screen being placed at certain points, know that that's the step we're leading up to where you go out to the car and the headlight doesn't work and you look at the diagram and you determine where to check and what to measure to do the diagnosis, right? That's the concept of the final exam. So in other words, make sure you lock in for this. Here we go. Normal operation. I think you guys can imagine. 12 volts comes from the battery in one way or another, goes to a fuse. So if we were to do available voltage measurements, 12 volts through the fuse, 12.68, I believe. Then it's going through a connector here. It's going to the switch, 1265. So it lost a tiny little bit right there, but that's because it's going through a little wire, a little connector, but it's losing very little to nothing. Goes to the switch. If we're trying to test these lights, you logically have to close the switch, right? So if the diagram shows the switch open, that doesn't mean you have to trace it with the switch open. You want to draw it how you want to test it. So if you're trying to test the headlight switch needs to be on, right? Duh, like that's pretty common sense. So we would close the switch, draw it closed. 12 volts should go through the switch, 12 volts to here, 12 volts to here, 12 volts to here. 12 volts split off, 12.62 to this bulb, 12.62 to this bulb, 12.62 to this bulb. This actually is the brake lights, now that I see it. If it's the brake lights, probably the reason I say this is the brake lights is this is most likely going to be the center high mounted, and these are going to be the two regular brake lights. In this case, it doesn't really matter because, again, how we test the system, it doesn't matter what the load is. It just matters that you can see how the load fits in, right? So we should have 12.62 volts all the way down to all three of these. Because if you notice, they're not wired in series, they're wired in parallel. They all have access to the full source. The full source was 1268. By the time it gets down here, it might be just a bit lower. If I were to simplify this, let's drop the last digit. It was 12.6, right? Look at that number, 12.6. It's still 12.6. It's still 12.6. Kind of makes sense? Then after it goes through the bulb, how much should it drop? If the bulb is working good and the circuit's working good, it should drop the whole source, right? We want this bulb to get all the power that it needs. We don't want this bulb to have to share voltage with other unwanted things. Make sense? So the bulb should drop about 12.6. Now, if we were to add that last digit back, it went from an 8 to a 5 to a 2 and then to a 0.2. So we may have dropped a grand total of, let's say, 2. Actually, that was 0.2. So that would be, we dropped from 68 to 62. So we dropped 0.06 unwanted. That's great. We just don't want to drop more than like a half a volt, right? We didn't drop 0.50, we dropped 0.06. This is a good circuit. Or for simplicity, drop that last digit. Just know it had 12.6, 12.6, dropped the 12.6 and left basically a 0 at the bottom. Cool. Now, what type of test might you do? Available voltage or voltage drop. So if it was available voltage, 12.6, 12.6, 12.6, 12.6, 0, 0. If it was voltage drop, you do like, let me voltage drop maybe the bulb. If I voltage drop the bulb and the bulb drops 12.6, that tells me the whole rest of the circuit's good. Get what I'm saying? Two different types of tests. What types of faults? Maybe there's an open in the series part. Where would the series part be? Now, technically, this is not a series parallel circuit, but there's a series part of this parallel circuit. Where would that be? Yeah, exactly. So that's up in this section. If I have an open up in this section, what's it going to cause? Which bulbs are going to be an up? All the bulbs. Bingo. Exactly. If I have a fault in the parallel branch right here, what's going to happen? Just that one bulb. Exactly. You're onto the concepts. This is nothing new. It's the same stuff, but applied very specifically. So at the end of this, you should be able to do a diagnosis on the car. If we were to have skipped to this and blew through the first 16 weeks, I'd be like, yeah, let's just cover this. Right now, you would not be tracking, I can assure you. You'd be like, I don't know. All right, so we've built up to this moment. We could have high resistance on the positive. So that'd be high resistance up here. If it was high resistance up here, you would not have a full 12.6 available. It would have dropped something before it. You could have high resistance on the ground side, which would mean you'd have 12.6 available, but you'd have voltage left over because it's saving it for the unwanted resistance on the ground side, right? That's another type of fault. Or we could have a short to ground, and that short to ground could be anywhere. These are the types of faults that you're going to encounter in the field and on the final. All right, so here's available voltage, for example, if you recall. Available voltage, we hang the negative on a known good ground. And then we poke the positive at various points. We have 12 volts, 11.9, 0 volts, 0 volts, 0 volts, right? You're probing different points. Before the load should be about 12, after the load should be about 0. If we were to trace this, we would have red up here and we would have green down here, right? So if you think in tracing, tracing is going to give you what your voltages should be anyway. That's good. If you would just want to predict it, you just know 12 volts before the load, 0 volts after the load, assuming the switch is closed. And again, we're going to be testing it in the position we need to test it. That's your available voltage. Okay, everybody remember that one. Available voltage, you stab the ground where it is, and then you just go around poking the red thing everywhere. Here's a voltage drop. The voltage drop is the T-Rex arms. You want to voltage drop a thing. What thing do you want to test? In this case, the bulb. So you put the red lead with your T-Rex arm before the bulb, and you put your black lead with the T-Rex arm after the bulb. What are we testing right now? We're really only testing between the red and the black. What do we expect to get right there? Yeah, exactly. And if we get 12.6, that tells me basically nothing's dropping up here and nothing's dropping down here. So I know that the rest of the circuit's good, right? Either one of these you're allowed to do. Now on the bottom one, if I wanted to test the switch, because I thought the switch could be bad, I could do voltage drop test on the switch. A switch shouldn't drop much voltage. So a 0.05, that's great. Remember, on an individual component, we never really want more than like a 0.2. Not 0.2, but a 0.2, 0.20. That would be like the limit. Make sense? So if I were to come over here and I were to get a 6-volt drop on the switch, I'd be like, oh, it's got a bad switch, right? So different ways to do some diagnosis. And generally, you can do either one you want, but I'm going to be asking you to do one and the other or the other. You have to be able to do both for me. Then when you get in the field, you can have a favorite like me. My favorite is available voltage. But at any point, I can do voltage drop all day. Like I can do right-hand batting. I can do left-hand batting. I can do normal snowboarding, or I can do goofy, but actually really not that well. Right? You got to be able to do both, even if you have a favorite. Cool. So we talked about if we had an open in the series, right? The measurement would look like this. 12, 12, 12, 12, all of a sudden 0. You know the open is between the 12 and the 0, right? The only time we should drop from 12 to 0 should be across the load. We should not drop from 12 to 0 on a connector. That's an open on the connector, right? The other way we could measure that is we could literally voltage drop it. So if you voltage drop the switch, it says 0. If you voltage drop the connector and it says 12, you're like, why in the world am I getting a 12-volt drop on the connector? That connector's open, right? Either method will find the fault, right? And yeah, obviously it would make none of the bulbs work, but if you knew that none of the bulb worked, you knew it would be up in this part of the circuit. We established that last time, but now you got to actually measure it and prove where it is. If you can tell me it's at this connector or it's between the fuse and the switch, I'm good with those answers. If you just tell me it's somewhere up in this side of the circuit, that you're not close enough. You got to basically get it to an individual component or between two connectors. So if I have a connector here and a connector here, if you can tell me it's between this connector and this connector, that's great, which pretty much that's the switch, but that's great. Cool. Like we talked about, if we had an open down here, we know that this one bulb would be an op, but how would we measure it? We'd get 12, 12, 12, 12. You get 12 over here, you get 12 over here, but you have 0 down here. You'd back it up to this splice, and you'd be like, I got 12 at the splice, I got 0 at the bulb, it's right in here. That would be a correct find. That would be good. Okay, makes sense. That's how close you have to get it. You don't have to be like it's at this exact point, but if it's between whatever that number is, B15 and the bulb, we're good. That's as close as you need to be. Cool. Good. B15, yeah. I would have liked an S15, but yes, if you say B15, between B15 and the bulb, we're good. If you say between B12 and the bulb, that's not good enough because that tells me it could be here or here. I want it as narrow as possible between B15 and the bulb. B12 is not precise enough. In fact, if the open was here, that would be a full misdiagnosis because that would have caused both of these to be getting 0 volts, right? So that'd be good. And I got a little bit more instructions for the final specifically, but right now, high resistance, if you guys will recall. So some of this is just a bit of review, and then it's going to be applied really well. If you remember, high resistance won't give you a full 12-volt drop. right here we had 12.6, 12.6, 3.5. If it was an open, it dropped to 0, right? But it went from 12.6 to 3.5. So what's that tell you it is? We know that, I think it's right in this switch, but it's corrosion, it's high resistance. So we just defined an open is an open and a high resistance is a high resistance. So if you say this is open, I'm going to say no, because you still have 3.5 volts. If it was fully open, you wouldn't have 3.5 volts carrying through. High resistance is correct. Open is incorrect. You might be correct on the location. You might be like, hey, I know it's in the switch, but like you need to describe it right. Right. So that would be, the switch would be the noun, and the, what's descriptive? Adjective. Right. So you use the wrong adjective there. Open is different than high resistance. I don't know if you remember this, but like on the very first 1 or 2 days, I told you I have a service advisor who'd take my diagnostic stories and he would just try to rewrite them. And I would say high resistance on the switch, and he'd be like, the switch was shorted. And I'd be like, no, it was not shorted. He'd be like, well, whatever, the switch is bad. And I'm like, the switch hasn't misbehaved. Like, leave my words alone, man. I need to be able to hold up in court. It was high resistance. High resistance and high resistance, that's what it is. It's just specific, right? Good. High resistance on the ground. We got 12, 12, 12, 12, 12, 12. After the load, we have 10. And you're like, what? Is that shorted to power on the ground? No, that would be an indication that we have a problem on the ground. But if it's got 10 volts left over, that means there's high resistance on the ground, right? The bulb only consumed 2.42 volts and it left 10.2 volts for the ground. That's because the ground has even more resistance than the bulb. That's a bad ground. Bad not being a great descriptor. That ground is high resistance being a better descriptor. Cool, kind of makes sense. Now, if we had 12 volts, 12 volts, 12 volts, 12 volts, 12 volts, 0 volts, that would be an open ground. Bit different. How about if we had a short? If you had to diagnose a short, this is how I would do it. Other manufacturers of special tools and things have different ways. So if I wanted to diagnose a short to ground, I would do it exactly this way. I would take my fuse out. You ready? This is going to seem crazy. I would take out the fuse and I would plug in a big headlight. Is that crazy or what? I'm running this circuit with no fuse. Do you want to know why? If I add a big headlight, the big headlight becomes the load. You follow what I'm saying? If the big headlight becomes the load and the big headlight lights up, you know what that tells me? That means I've got 12 volts on the positive side and I've got a good ground on the negative side. That's the only thing that would make that big headlight light up. So at that point, this is the best way, and it's also the fastest way. At that point, what I would do is I would come down here and I would start disconnecting things. If I disconnected the ground and the bulb stayed on, that means the problem is not down here. If I disconnected this connector, B28, and the bulb stayed on, that would mean the problem is not down here. Kind of makes sense? So if I were to run quick, well, I think you can follow me. If I disconnect this, clearly this stuff is not the source of the ground. How do I know it's not the source of the ground, though? Let's see if you got this. The bulb is still on. If the bulb is still on, there's still a ground somewhere. But if this is disconnected, apparently the source of the ground is not down here in this mess. That would mean the ground must be up here. So if I went to this point right here and I disconnected it and the light went off, I just took the ground away, correct? So if I disconnect it here and it makes no difference, but I disconnect it here and it goes off, I know it's between here and here. Did you follow what I'm saying? Right? I'm disconnecting things as the potential source for the ground. If I what's a little crazy though, if I disconnect here the light would go off because I've eliminated down here. So if I were to just go ahead and I were to disconnect up here and it went off, I'm not done. I got to plug it back in here. I got to go down here, disconnect this one. If it still goes off, I'm not done. I got to plug it back in. I got to go down here. It still goes off. I got to go down here. I disconnect it and it doesn't go off, right? It's the difference of where it does go off and it doesn't go off will tell you where the ground is. Potentially, or like a lot of times what we'll do, we'll call it the split half method. We'll go to the middle and just disconnect the middle. Boom. If I were to disconnect this one, boom, and it were to go off, I would know it's after this one. I wouldn't have to waste any time up here. I'd know it's down here. So if I split it in half at this one and I disconnect and it goes off, it could be any of these down here. So maybe the middle between this and the bottom is this one. If I disconnect this one, it does not go off. I'll be like, all right, it's between this and this. I could narrow it down just a bit quicker. Split it in half, then you know which half it's in, then split that half into half, and then split that half into half. It's statistically, on a diagram at least, the quickest possible way to find it. However, in real life, if this thing is really hard to get to and this thing is really easy to get to, I may go for what's easy, just because like the split half method is perfect on paper, but if this stuff is hard to get at, maybe it actually makes more sense to not pull all the interior panels and the dashboard and all this stuff, but if you follow the logic, you'll get it. You may be slightly quicker or slightly slower. And remember what we talked about, a lot of this is about efficiency, right? The more efficient you are, the more you can bill. And with the attitude of like, well, I'm going to try to milk this job out because I'm paid by the hour and my boss makes too much money or whatever. That's not a good attitude to have in this business, to be honest. Probably a pretty good attitude for like fast food though. But in this one, if you can be very productive, you can work on more cars and you will most likely be incentivized to work on more cars and paid accordingly, hopefully. That's the design anyway. Uh-huh. Sure. Correct. Yeah. You need you make your own, you get a big headlight bulb. Like this little incandescent's not big enough, right? But if you got like even a halogen bulb and you make your own little jumper wire and you pull the fuse out and you plug your jumper wire into the fuse, kind of like this. If the bulb was up here, I'd plug this into the fuse positive and into the outgoing part of the fuse, and then it lights up. I just disconnect stuff and I keep looking at the bulb. Oh, it went out. Let me back it up. It didn't go out. It did go out. It didn't go out. It did go out. It's between the two. So it's simple. No DMM needed. Don't need it. Don't want it. What you don't want to do is blow the fuse and then put another fuse in and blow that fuse and put another fuse in and blow that fuse and blow that fuse. And if you got a big old pile of fuses, you need to trade that in for a big headlight and some leads. That's what I'm saying. Now, because we're talking about on the car, right, I just showed you, on the paper, it's one thing, but on the car, connectors aren't always easy to get to. Also, that you might want to check some of these points like back here, right? You want to check this point for 12 volts. On the car, here's what that looks like. If you want to actually test the vehicle, you got to go to the connector, like this style connector. And then you're going to have to do something like, if you want the cheapest option, you could buy these right here. Prim Quilting, 35 quilters T-pins. This was like the dollar store or something. I mean, we're talking cheap. I could literally just cut this open. This was like $1. And I would give this to you, but truthfully, I don't trust you enough. We've got the most basic little T-pin. Now, what I'm going to do with this basic little T-pin, you see this little basic T-pin? This is like no money. Is like the picture shows, I'm just going to pick which wire it is based on the wiring diagram that you covered. So let's say I think it's the purple wire. I'm just going to slip this one in, and I'm not stabbing it. I'm making contact, okay? So I've got this one back probe. I'm going to pass this one around. I'm going to start right in the front. You guys can just take a little look at what I've done. You can feel it. You can practice back probing a bit. That's good. Essentially, all I did was I made connection with the terminal. Remember how we did some terminal practice? I'm not stabbing the wire, breaking the insulation. I'm just making this metal touch this metal or copper or silver, or whatever, gold, whatever it is, right? That's it. That's how you actually back probe it. So when we're looking at this and we're thinking about the boards, like those are really easy to get a test point. When we're looking at this, I mean, it's not really that hard, but to know which wire, do you remember how I'd know which wire? Wiring diagram, right? So if I were to look at this one, I'd be like, oh, the green wire going to the bulb, which is terminal 3. Then I could look at the connector and I'd be like, oh, it's actually this one. I need to probe that one. So there's several skills that you need to know leading up to this point. Go ahead. Yeah. Just a way to get a voltage reading. All right, we'll back it up one and then I'll get it. Let's say that this bulb, let me pick one that was an open. Let's say this bulb doesn't work, right? Follow me? If this bulb doesn't work, I kind of want to know if it has 12 volts getting to the bulb or not, right? Follow what I'm saying? So let's say the bulb is in op. You wouldn't just randomly probe stuff. You'd start with a symptom. This middle bulb doesn't work. I want to know, does it have 12 volts going to the bulb? I would look on the diagram, and then that's where I was kind of picking on, let's say, I mean, any of those, right? So let's just say it's the green wire. Then I would go to that connector, and I'd be like, oh, I'm going to go to the green wire. It should have 12 volts right there. See what I mean? So why would we probe that one? Because I looked at the diagram, I studied the diagram, and I knew I want to see if it has 12 volts right there. And then let's just say it does not have 12 volts, right? Because I do my back probing, I check right there, it has 0 volts. Now what I would do, and that's actually the next thing we're going to cover, is the next thing I would want to do is I need to go to B15, and I need to see if B15 has 12 volts. So you got to put your GMM on there. Yeah, bingo. Gotcha. So that is how we would probe it like this. Because the light's in op, I would T-pin it. Because you see, we're showing the probe right there. Now I understand your question better. We're showing the probe right there, but think of the size of your probe. I'm going to do something that I'm not going to allow you to do, but I'm going to do it because I can. If you want to probe this, right, and you land your black lead on ground, and you take your red lead and you're like, ooh, let me test that connector, and then, well, you guys got the connector. I was thinking if I could find another little connector, but imagine the sensitivity in that connector and you're like, yeah. I mean, that's not nice. The purpose of the T-pin is just simply to give you a nice clean access point. And it shouldn't stab the wire. Like this right here, I'm going to pass this around. This would be a no-no. But this, I'm going to do this because I'm allowed to. I could unthread this and I could be like, oh, it's the green wire, remember? I could slip the green wire up in here. I could do a horrible thing that I never do, and I'm going to really have to ask for your forgiveness. Do you offer it? I just stabbed this wire. But it will get a nice reading. So now this is on here and it's firm. It doesn't pull off. I mean, it's kind of convenient. I'm not going to lie. This thing just probed it. However, when we talk about wire and terminal repair, why is that a problem? That's going to become corrosion. That's going to become unwanted resistance. Today, no. In a few years, yes. They'll be like, what hack job worked on this? They poked a bunch of holes in the wire. So we don't go along poking holes in the wire like that. What we really want to do is back probe a terminal. And that's kind of what I was saying. If you're back here, I don't need to know if the open is right there or if the open is right there. I just need to know if the open is after the switch and before the connector. If you want to know the exact millimeter point, you'd have to stab the wire. We don't do that. That's not good. Kind of, right? So you can see that. Now the T-pin is a good option, but wait, there's more. This is a back probe set, pretty nice one. These are cool because they actually can connect right to your meter lead. So if I connect this to my meter lead, rather than having this, I don't know, like if you were going to get a mani-pedi, this would be like the nail tech pulls out a chainsaw. Like please get that chainsaw away from my feet. This is the tool for the job, right? This one is a killer, and this one is like, I can just, but what's cool is it'll actually connect, and this might not be the right type of lead. This is for a fluke, but if it's for the right type of lead, it'll actually clip on, and now it's just like this. You could probe it here, probe it there. Like a really good electrical tech, they don't even use these. They'll have these type of little back probers on all the time because that's mostly what we do. All right, so if you picture this one, this and the T-pin are just about the same. We'll slide it and back probe. Good. If you want one on the red and one on the black, we can do that. So especially if you want to do a voltage drop, you could put your red lead and your black lead really easily right on the different parts of the connector, whatever. Technically, let's say that it was this connector. If you wanted to test this connector on the blue wire, you could put your red lead on this side, and you could slide your black lead right on the other side of that connector and actually measure what is the voltage drop of that connector. Cool. So that's how we get on the car. That's how we do the on the car diagnosis. Here's another option of a nice back probe. These are from Pico. These will connect right to the picoscope. Right. So Fluke has some, Pico has some, AES Wave has some really cool ones. Another very interesting concept is, you remember when we want to check amps, right? You need to open the circuit. Like think about how could you open the circuit? You have to cut the wire. All right, so this one's going to trip you out. If I wanted to measure amps and send it through my meter, right? Because it's in series with the meter. Remember that? I could go to this connector, and let's just say this connector has 4 male terminals on this side, 4 female terminals on this side. I've got a lead that I can probe in there. This one can go to the male side because it's a female terminal. This one can go to the female side because it's a male terminal. And I basically open the connector up and put this as an in-between, and I can keep the connector connected, but one of them I could have like this, and I could actually measure amps or, you know, send it through my meter or whatever. So this is a really cool, this isn't exactly a back probe, but it's a terminal kit so that I can get a reading while keeping the connector connected, because I can intercept the male and female. That kind of makes some sense. So I'm going to pass this around as well. This would be another type of a kit that we may use, especially when we get more into the advanced body electrical stuff. That's another thing you could do. That's a pretty good option, actually. If you're good and you can do it carefully, you could unpin the blue and unpin the blue on the other side and then pull them around and do the test. That's another way. But if the terminal gets damaged, then you're like, maybe I should have used the adapter. So all those are fine. You just got to be careful, right? Don't do it. This one, I did it as a demo. That doesn't mean you get to do it. This was an experiment for class. And also, do you know what this is called right here? It's called front probing. So I know some people, some corporate trainers, like corporate trainer at Toyota, if you get caught doing that, you get kicked out. And your dealership is paying to have you sent there, and they send you home, and you got to go to your boss and be like, oh, I was at the Toyota training center, I got kicked out. And they'll be like, what'd you do? And you'd be like, well, I front probed. What else was I supposed to do? This is like, you just stabbed that terminal. That terminal is supposed to be a nice, tight fitting square, and now it's a blown out crater, right? So that's really bad. However, I'll be really honest with you, because I like to be. Sometimes front probing is the best option. So the way that I would front probe this, I'm saying it off camera. Well, actually, I'm saying it on camera, aren't I? But I'm saying it unofficially. And I will, if you twist my words, I'll defend myself. If I had to front probe for one reason or another, what I'll sometimes do is I'll take a little piece of wire, like a small wire, and I'll strip the insulation off, and I'll take maybe just a few strands, right? Just a few soft, little delicate strands. I'll twist them together, and I'll make it so that those little strands will make a contact on the front side. That's fine. You're not going to hurt it. if you're not shoving something in there and deforming the metal, there's technically nothing wrong with front probing. They don't make very good front probing kits, but there are actually a few. So this, for example, would allow a front probe. If this is the exact terminal that's made for the female, you can use a male front probe kit. So if you do want a front probe, you can. This, however, is not a front probe that's acceptable. This is a T-pin rammed into a terminal that's too small for the T-pin, right? This is a no. This is a no for the insulation damage. These would allow you to front probe, but there's like 100 different size terminals. So if you want a front probe, you need 100 different adapters. I like the idea of stripping the wire and using a few little strands, just enough to make the connection. It's non-invasive. It doesn't damage the terminal. That's the on the record answer. But if you're like, yeah, you said you could front probe it, like this, there was more words that I said. Okay, don't separate what I said from the other words. Okay, cool. And then just for fun, I'll give you guys these links, these different front probe kits and different options. Okay. I like it. It's cheap. Kind of steady. Yeah, I mean, if you got it just the right size where it'll just put a slight amount of tension, you don't really need that steady of a hand. If it's too big and you have to force it, it's a no. If it's too small, you need a steady hand because it's touching and not touching stuff. But if you get it, like if it's just a little loose and you add one more strand and you can just get it where it just has a tiny bit of drag, no, it'll hang there. It's pretty, I like it. I made it up and I did it the cheap way, right? When I was first entering the field, I was looking for all the tools. And then once you make a lot of investment, then you're like, all right, let me get a return on the investment. So every tool I don't have to buy is more money I can put in my pocket, or my retirement plan, or race cars, or motorcycle stuff, or parts upgrades. I need to put right. The less I invest on a special tool, the more money I can put into things of whatever I just said. You know, whatever your choice is. In the gas tank, whatever you're talking about. Was it an IS, what were you saying? An LS. Yeah, in your V8 gas tank deal over there, right? So that type of stuff. So I like the twisted wire, method, but these are nicer. I'll admit, it's just more money. All right, so the rest of this is going to be directly applicable to your final. It's going to be very specific, and I've put up more than enough of these to cover, so I reserve the right to be like, nah, we'll back off on this a little. I threw a ton of them up because I want to kind of gauge how you guys seem to be reacting, right? So this is going to marry testing like this with a basic diagram and a specific EWD, like a real actual wiring diagram. This has terminal numbers. This has test points. You can expect your final is going to be just like this. So you didn't need to know wiring diagrams to measure to do this, right? You can just follow this. This one is an actual full diagram. You have to be able to interpret a diagram, look at terminal numbers, etc., right? So if we were to say headlights, don't turn on, your first step in this type of on-the-car diagnosis is you got to know how the circuit works. You got to know where the components are. You got to know what wires. Like, I don't know. So if you were to say, oh, the headlights on my blah, blah, blah car don't work. Like, I don't know where they start. I don't know where the fuse is. I don't know where the connectors are. I really don't know anything about it, right? So the first step is we start with the diagram. From here, what I would normally do is trace it. You guys remember when we did a lot of tracing, right? So if I were to start with this diagram and then trace it, we'll trace a later one. This was just to give you a demo. 12 volts comes off the battery, right? 12 volts to the fuse, 12 volts to the relay, 12 volts splits over. This coil is the load, right, on the control side. So I don't have 12 volts going through. This should all be ground. Now I know a little bit more about the circuit, right? And then if this is ground, the ground is provided by this switch, combination switch. And if the combination switch provides the ground, that should magnetize the relay, close this contactor. Now 12 volts should go out on the white wire, right? So The first thing we need to do is pull the diagram and understand how this particular thing works. We don't pull the whole car diagram. If it's the headlights don't turn on, we just get the diagram for the headlights. Now we know kind of how it works. Now, if you're in the backyard or whatever and someone says my headlights don't work, you could probably wing it a little bit. Like, you know, the headlight needs 12 volts and ground, but if the headlight doesn't have 12 volts or it doesn't have ground, like, you don't really know where to check next, right? So if somebody says, yeah, can you diagnose XYZ problem, or can you walk me through it? It's like, how? I mean, if you want me to walk you through the diagnosis, I got to get the information. I got to pull the wiring diagram, and I got to tell you, check connector, let's say check splice I13, and they'd be like, what? You know, so like, it's not as simple as on the boards, you know, and every car is a little bit different. So you got to be pretty involved to get to this point. So if we were to look for, let's say, the left and right stop lamp are dim, but the center high mount is normal, I could probably evaluate this a little bit. The left and right are dim, but the center high mount is normal. Well, if the center high mount is normal, I'm going to say it really can't be any problem up in this area. It's got to be a problem after where it splits, right? Before it splits, that's kind of like the series part of the circuit. If I had a problem over there, it would affect all three. But if this one is good, then that would mean the problem's probably between here and probably here, actually. I bet you it's just right in there. Because if the problem was here, it would only affect the left side. If the problem was over here, it would only affect the right side. But the left and right both would be up in here because the center high mount's normal, right? So the next step, once you start to understand the system, is start to determine what you need to test and what you don't need to test. Brand new technicians tend to want to test everything. But remember, everything we test is time. And everything you test is time somebody's got to pay for. So either A, that's your boss. And your boss is like, I have to pay you 8 hours to diagnose a basic electrical thing because you want to probe everything. What'd they teach you in school? And I'll be like, I didn't teach them that. It's not what I taught them. Or if you are billing so your boss is going to eat it, right, and pay you. Or maybe you or your boss is going to be like, hey, customer, yeah, you need to pay like a whole bunch of diagnosis because it took us a long time to test everything. You could do that. That could be profitable. But what's probably going to happen is the customer is going to talk with the shop down the road and be like, yeah, you paid 8 hours to have your headlights diagnosed. That sounds excessive. Like, we usually do it in 1, and sometimes it's 2, and the highest we've ever had is 3. So like, if you paid 8, yeah, we could probably save you money. You're losing business, right? If you're working for the company, that's not good for you because that's your job. You might lose your job. If the company is yours, you're losing business. That's your profit. So you want to be efficient. You don't want to do any more tests than normal. And the other thing is, everything you test, you got to take stuff apart, and you run into like, hey, if I had to pop a panel off, clips may be brittle. It's an old car. They may break. So you're just opening yourself up to more and more problems. Kind of like a surgeon. The surgeon has to fix your knee. The surgeon doesn't want to open all this stuff up because there's more potential for things to go wrong, right? So if I look at this and you understood what I was saying, I know the problem is going to be down in here. I want to only test down in here. I don't want to test over here. I don't want to test over here. I don't want to test over here. It doesn't make sense to test those spots because remember, the center high mounted stop lamp is normal. So it can't be any of this stuff. It's got to be over here. And the 2 bulbs are dim. So actually, technically, you know what? That's interesting. It could be on the ground side over here, but it wouldn't be over here. So I would narrow down what exactly I need to test, and then I'd do a test that makes sense, right? Not be testing other random stuff. Cool. So this will be like one of the last how-to tests, and then we're going to do some walkthrough tests. Parasitic drain, you guys know we talked about that a little bit with battery. If you were to go try to do like a parasitic drain test, you know there's going to be some normal drain. voltage regulator, digital clock, keeping the ECM, keep alive memory, sometimes maybe storing the seat memory, these types of things. Generally, they should not exceed 50 milliamps, but that number has been recently up to like 75, right? To actually do it like we had talked about, you would go ahead and you'd put your black lead. You could do it either side really, but if we're going to do the ground, you could put your black lead on the actual post, your red lead on the terminal, and they'd be touching, and you'd have basically 0 amps going through your meter because all the electrons are going to go directly. Then what you do is you'd actually slip the lead, slip the clamp up. The whole time you never broke contact, right? So if you check this, right there, all the computers had the contact to the battery. Right here, you disconnected it, but look, all the computers carrying their electrons over here are going to go to your red lead through your meter and out to the negative terminal. If you do it like this, you never break contact. The reason we do it like that is because if you never break contact, the computers don't all of a sudden all have to wake up. If you disconnect power and then plug it back in, all the computers are like, all right, check in. What's happening? We lost power. Where are you at? What are you doing? All right, so if you notice right there, that was a pretty cool little trick. Make contact the whole time. They do have some tools that allow you to do that. Then, of course, you'd measure the lead. So we talked a lot about parasitic drain, but being that we're in body electrical, I can show you what we do on the car. This is pretty applicable. Now let's say we get into some more of the diagnosis. If you are doing a parasitic drain on the car and you find out that it was, remember how we talked about how you could pull the fuses? So here you get a number, cool. If your number is too high, that one would be a pass. If your number, actually that's 230 milliamps, that's too high. That's a quarter of an amp. If your number is too high, then what you do, you could go to the fuses. Let's say you pull fuse, pull fuse, pull fuse. When you pull the 7.5 amp fuse, all of a sudden you get into spec. That means it's on that fuse, right? Well, in the system, you can find out all of what's on that fuse. So in the 7.5 amp dome light fuse, you have the clock, the garage door opener, the interior light, unfortunately, one of the communication systems, and the wireless door lock control. Then you would have to narrow down how to eliminate each one of those. But you know that your problem's within these 5 things. You're not worried about engine control because that's on a different fuse. Cool. So this is getting on the car, how we do the diagnosis just a bit differently. Cool. And then another thing you must know is if we have bigger diagrams, a lot of times there'll be like a main power source. This is a junction block. So we'd have a whole bunch of fuses in there. If you have to trace it back, you got to understand this fan relay fuse ultimately is getting its power from this wire, which also feeds some other things. So if you had a problem with, like, let's say if I were to look at this, the wiper and the fan relay and whatever this thing is, I don't think it's going to be these fuses. I think it's going to be this. Oh, what's that? That's the 10 amp ECU ignition, right? So sometimes you got to get actually on the diagrams that go in the fuse box. All right. This one we were talking about the ground. I think we were probably decent on that one. You guys can see the test though, right? We put the big headlight and we disconnect some stuff. So like right here, your headlight's on. So that means there's a ground somewhere down here. Then what did we do? We disconnected. Remember that lesson? But now on this diagram on the car, what did we disconnect specifically? 2G right there is the connector, right? So the concept is the same, but exactly what did we disconnect? We disconnected connector 2G, not connector 2M, not connector 2K. We disconnected connector 2G. Cool. And then over here, we connected 2K, right? So depending on what the fault is, you can disconnect each individual circuits, but what you got to understand is on the car, you have to relate it to a specific connector. Connector 2G, connector 2M, connector 2K. Now, if we were to jump forward on this one and we were to say, what if I wanted to check the voltage right there? 2G is the connector. What do you think 15 is? 15 is the terminal number. So if you want to actually do the test on the car, you go to terminal 15 on connector 2G, and you could test the voltage. And that's the direction we're going with the diagnosis, right? So let's say we go with, I'm going to jump right over to this one would be pretty good. Right here. What if I were to jump on, how about, this one's kind of interesting. This is a feedback problem. If you were to go up to this car, you'll notice this is on, this is kind of dim, this one's kind of dim, and this one's really bright. That one would be a little bit confusing because you'd be like, how is this one too bright? Well, this would cause what's called feedback, whereas if you had an open ground and it has a way that it can make it through, you're going to have electrons go through here. They should go directly to ground, right? But like if I were to trace this, can you see how they can't go directly to ground, right? They don't go to ground in the way they normally would. You're going to go, we'll do the color right here. There's my mouse. Let's pick positive, we agree. Positive will go to here. Positive would go not down there, but over here. Then after the load, it would be ground, right? The ground should have gone over here, but it can't. So where does it actually have to go? It's actually got to go this way, this way. So green is not even the right color. It wouldn't be green yet. It would actually become like not 0 volts, because if you look at it, it's going through this one and then through this one, then through this one. So all three of these now become, technically they're in series. Do you see that? This one's going to take some, this one's going to take some, this one's going to take some. And then actual ground would start down here. Right? Kind of crazy. So now do you see why these three would be dim and this one would be bright? This one had a good clean ground and a direct positive. These three all had to share 12 volts. So you get 4, you get 4, and you get 4. That one's kind of crazy, huh? To think of why 3 bulbs would be dim and 1 would be bright. You'd be thinking there's 3 problems, but it could be just as simple as 1 open ground. So that's the type of thing that you'd see. Right? And then if you were to walk that through, you'd notice pretty much we traced it, but that's what this would be saying. If you were to measure that in voltages, you'd get like 12 volts here, 2 volts here, 1 volt here, 1 volt here, 0 volts here. You'd be like, what is with all this voltage? It can seem very confusing. Then if you really break it down and you realize what's happening, because this ground is open, this one, and this one all have to share voltage. That's why you're going to get numbers all over the place. I probably would have went with 4, 4, and 4, but because these are different type of bulbs, they're going to drop different amounts. They have different resistances, right? So it's an interesting one. Okay, and then if I gave you probably one really good guide on how I would do this, let me jump right up to where I want to be. Not this. Nope. Let me pick one so that we can walk through how a diagnosis will be. A full, thorough diagnosis. All right, let's say we do this one. All right. If this were the simulator, this one was headlights do not turn on. The first thing you need to do is understand this. And if it was on the car, you could trace it, right? But let's just say we wanted to, you want to trace it? Would tracing it help you? Kind of, or no? We could do it. Let's start with the positive. Let's go with 12 volts out of here. We agree, right? Goes over to here, goes to here, splits off. Okay, then from there, we can do the ground, and that's it. Now, if the headlights don't turn on, what should we do with the switch? Yeah, turn the headlights on. So that's what we're going to do. This goes up to here. We have the headlights on. That's what that means. Goes over to here, goes over to here. Okay, that's significant. And it also goes down here. And this is not really that important, but we can do it anyway. Now, if we have 12 volts and ground, what happens to that relay? Yeah, it's gonna be the load. It's gonna activate, which is gonna close the switch, right? If it closes the switch, what's gonna happen? 12 volts should go through and go over to here, right? So you may not be able to exactly trace it on the. I gave it away a little bit, but the final is a simulator. So you're gonna have something just like this. You're not gonna be able to trace it. What you are gonna be able to do is measure it. So if I were to go ahead and clear the drawings, if I were to take my black lead and I were to put my black lead down here, say I were to do that, take my black lead, put it down here on the ground. I were to take my red lead. Let's see if you remember, what should I have right here if I have the headlights turned on, just like we tested it? Remember the drawing? I should, but if I have 0, what should I test next? Yeah, maybe I should go over here, and you could do that, right? On the simulator, you can. This is exactly how you diagnose the car, right? And then if you have, let's say if you had 12 volts above the switch, but 0 volts below the switch, you'd be like, huh, well, I wonder if the relay's working. You could test this point with your positive. You could put your positive here, and you should get a ground. But if I have no ground right here, then I would move my diagnosis down into here, right? So what you have to understand is on the car and on the simulator is exactly like the car. You have to actually know the connector numbers. So if we were to zoom in onto that, and this one's a little, probably just a little bit too small, but if I were to zoom in, I don't know if I can, but if we were to zoom in, this one's perfect. If I wanted to test at this point, what am I actually testing? Connector 1D, okay? Terminal number 5. If I want to test this wire, I got to find connector 1D, and that can be, you're going to have to dig around the service manual a bit because we did cover that somewhat. You'd have to find literally connector 1D and then terminal number 5. And then if I were to jump way back to here, if this was connector 1D and this was terminal number 5, this is what you do with your probe. You'd slide it in there. Every one test you have to do, you got to understand why you're going to do the test. Does the test make sense? Locate the connector, determine which terminal it is, which was kind of a previous lesson, right? And then actually insert your T-pin or insert your back probe, boom, and then you can get a measurement. No stabbing, okay? And if you can determine from there, all right, I was supposed to have 12 volts right there, but I didn't. I had 0 volts. Then you would move on to where you should check next. And eventually you're going to find the source of the problem. And then what your write-up is going to be is something more like, right, if we were to look back at that one, if you were to say, I think I had it right about the one that was zoomed in really nice was right here. You could say it's an open between connector 1D terminal 5 and connector IP3 terminal 2. You're done. If you even wanted to throw bonus points in, you could be connector 1D terminal 5 and IP3 terminal 2 on the RL wire. So that'd be red and light blue wire. That'd be like, boom, you got it perfect. That's like the ultimate goal right there. If you can do that, you're good. Okay, so that'll prep you for what's on the car, which we're about to go do, and what the finals and beyond. However, just to give you the preview of why we're covering non-ECU controls, even though most lights are now ECU controlled, is you got to kind of focus on the basics of how to test it with your meter, but to not leave you totally in the dark, because you may take electrical 2 like I don't know when, another year, never. I'll break down the differences. Electrical diagnosis, it's you and your meter. You don't use the scan tool. You don't use active test. You don't use data list on the scan tool. A lot of times it only affects one side of it, right? Whereas when it's computer controlled, it affects more. It could be high resistance, which is an open, low resistance, which could be a short or a failed component, right? So if we isolate this, when the car comes in with an in-op, whatever, headlight, power window, whatever, it's going to be an electrical fault, and it's going to be either an open / high resistance, a short, which is also like low resistance, right? And that would be repairing the circuit side, or it's a bad component, right? So if it was the bulb, it could be the bulb, right? That's a bad component, but it could also be an open in the circuit or a short in the circuit, basically. And an open would include high resistance as well. It's a resistance problem. Cool. Whereas when it's electronic, computer controlled, the ECU controls it. So all of a sudden now you're worried about the ECU. So it could be the component or it could be the wiring. And the ECU is an additional component, but it's a component that does a lot of different things, right? When we go to test it, we're not probably going to use the meter as much. We're going to start by checking for inputs. We can command things on and off. I'll just show you. So if you did an overall, this is the system. Your body ECU controls your headlights and taillights. We agree? But to know what to do, it's got to look at your light control switch and your ignition switch. So if you turn your ignition on, the body ECU is like, all right, time to turn some lights on. What is the light control switch saying to do? You see what I'm saying? So if you back up way back here, this taillight switch is sending voltage directly to the bulb. If we're talking about this style, that light control switch doesn't power the bulbs. The light control switch is an input to the body ECU, and the body ECU ultimately controls the bulb. See how the diagnosis is just different, right? And then it is also going to reference the light sensor and say, is it light out? Is it dark out? So that way, if the driver doesn't know to turn the light control switch on, that's okay. The body ECU can look at the light and say it's dark outside and override the driver and turn the headlights and the taillights on when the driver is kind of crazy. Uh-huh.
Sure, I understand this. So it's the one situation, we have to turn the switch on.
That's non-computer controlled. Bingo. And on the ECU controlled, the computer controlled, you can, but if you forget, the computer does it anyway. Ultimately, the computer has the control, right? So I usually like to break it off at this point, but because I want you guys to like have a forward view of what you're going to need to learn on the electrical 2 and the computer controlled stuff, this is the system. If you wanted to check the light switch, first off, the complaint would be different. Like normally the customer's like, when I turn my headlights on, they don't work. Now they could still say when I turn my headlights on, they don't work, or they might say my headlights are on even though I didn't turn them on, and you'd have to be like, well, yeah, your body control module said that you should have them on, so you don't have a say. I'm like, but I want to control it, and in this system, ultimately the computer has control. Computer has the ultimate say. But most of the time that's good. The biggest difference for us as technicians is the way we diagnose it. So if you wanted to test this switch, you need to know sort of like how to go about testing it. Then you need to sort of know how the body ECU works. So how does that computer work? I got one word for you. There it is. Uses magic, magic smoke. We put magic smoke in there that does magic stuff. That's why if you short it out and smoke comes out, that was the magic smoke, it'll never work again. Do you ever wonder why when smoke comes out of electronics, it no longer works? because that smoke was magic. If you can get all the magic smoke back in there, it might work again. No, that's being silly talk. So how about in reality, if you have a switch, you turn on the switch means you close the switch. The ECU monitors the voltage right here. If it was 5 volts, that means your switch was open. If it dropped to 0 volts, that's because you closed the switch which connected it to ground. That's going to take that as an input, right? This input is like, computers don't know open or closed. Really, they know like 5 volts or 0 volts. 0 volts means the customer just turned the switch on. Then it's going to look at a logic. The ECU logic is programmed in by an engineer. The engineer says, oh, if that switch is 0 volts and maybe some additional thing like the light sensor is this and your speed is that and your battery voltage is this, right? They can program other things, not only the switch. It'll say, oh yeah, then what we should do is we should send 12 volts to the bulb, right? So the ECU looks at this as an input, and all you do as the driver is you control this little switch. Then if it likes the inputs, it can choose to send 12 volts to the lights or not send 12 volts to the lights. Make sense? So if you're diagnosing this one, you got to determine, is it on the input side of the circuit or is it on the output side? Do you think it could be the switch? Yes. Do you think it could be the bulb? Yes. How do you know? Well, let's go and look at the light switch on the live data. By the way, I gave you a preview of this. Do you remember how you checked a switch with the scan tool? I was giving you like a way earlier lesson, so now you can see on a modern vehicle, I'm not using my meter. I'm not probing. I'm not going to do the back probe thing. I'm going to go with the scan tool, take apart no panels, not probe anything. I'm just going to look at the switch. I'm going to turn it on and off, and it's going to show on, off, on, off, on, off, and I'll be like, okay, the switch is good. Get me? It's really nice. I prefer this, to be honest. And then from there, that tells me the input side. If the switch doesn't change on, off, I'm like, all right, then I probably will have to go with my meter and find out, is the switch got the open? Because it could be in the wire, it could be in the switch, right? I might have to go to the meter, but at least I can initially know if it's on the switch side. I don't have to test the switch with my meter unless it doesn't change the data list. If it doesn't change the data list, then yes, you're probably using the meter. All right, then from there, what if I wanted to test the bulb? Well, I actually have to go under active test, and this is when you have the bidirectional scan tool, and the scan tool can make commands, not just read. The scan tool can tell things to happen. I could go to the headlight relay and turn it to on, and I could test the output side, right? So if we were to look over here, I can test the input side on the data list or live data. I can test the output side with whatever the manufacturer calls it, special functions or output tests or actuation tests or active test, right? This turns things on and off. This side senses things that are being moved, basically, right? So that's a pretty cool one. Then if you get, more advanced in the electrical too, we start to have to do more things with like checking waveforms and voltages and frequencies. And really quickly, the meter starts to run out of gas and the meter's like, I don't do that. Well, we get into an oscilloscope, which is going to graph voltage over time. And so like, this is the type of screen you'd look for. You'd be like, this is a good waveform. Maybe this is a good one, or this is a bad one. And you have to actually interpret it differently, right? So quickly, the body electrical, this was basic body electrical, but the more advanced body electrical is like a whole different subject. So just so that you get a nice preview. All right, you guys should be probably pretty good to diagnose on the car, would you say? You think you can do this? Let us make a plan about that. I have a proposal for you. You like proposals? All right, how do I get this to stop sharing? Stop sharing. We are going to do stop the share and